Hello students, we are studying some reactions from the question paper of this asymmetric synthesis MSc second year class. Now let us see some reactions where the product is given and we have to predict the proper reagents and the proper mechanism for the reaction. So this type of the reaction generally asked in the question paper for 3 or 4 marks. So in this case we have to consider or we have to identify what will be the functional group change occurs in the molecules, and accordingly we have to give the reagent and the mechanism for the reaction. Now let us consider this first reaction. We can see here the structure of the substrate. It is the benzene ring further attached to the double bond. So double bonded compound is given as the substrate, and this double bond is get converted into the epoxide. So we have to think about which type of the reagents are used for the formation of epoxide from the double bond. So we know that for this per-acids are used. Per-acids are used with the carbonyl compounds also. The name reaction, it is the Baeyer-Villiger oxidation. So that will carry out the conversion of ketones into the corresponding esters or the lactone compounds. This is the first reagent for the lactone compound or oxidation. Here for epoxidation, so if the double bond is alpha beta unsaturated double bond, if carbonyl group is in conjugated with this double bond, and we have to convert, we want to convert it into corresponding epoxide molecule, then we have to use the hydrogen peroxide in the basic medium. So this reagent is suitable for the oxidation of this alpha beta unsaturated carbonyl compound so that this double bond can be oxidized to corresponding epoxide. So this reagent is selective for the alpha beta unsaturated carbonyl compound. Then we have, if this substrate there is no carbonyl group is present, simple double bond is present, and further we are getting only beta epoxide. So reaction is purely asymmetric. So we have to use the chiral reagents here, or we can use the chiral substrate. So substrate is already given. So we have to consider or we have to find the reagents that will carry out the asymmetric oxidation. Now in asymmetric synthesis we have studied different types of the oxidation reactions. Osmium tetroxide with the attached with the chiral ligands, when they are used thalazine based chiral ligands, or the DHQD system, quinone system or chiral ligand. So this type of chiral ligands in addition with reaction with the osmium tetroxide, that will carry out the oxidation to corresponding diol compound. This is first oxidation in asymmetric synthesis. Secondly, we can oxidize here to epoxide. It is the Sharpless epoxidation. So Sharpless epoxidation, only allylic alcohols are used as the substrate. So we cannot oxidize the simple double bond. Here simple double bond is given. So Sharpless reaction, it is possible for conversion of allylic double bond, allylic alcohols, especially allylic alcohols that containing allylic double bond, that can be oxidized to corresponding alpha oriented epoxide or beta oriented epoxide. So only allylic alcohol is the important case for this reaction, and titanium tetraisopropoxide in presence of the tertiary butox peroxide compound are used along with the chiral ligand diethyl tartarate. So that is condition for this Sharpless epoxidation, which is not applicable here. So we have to find another oxidation. Third is the manganese saline complex. So manganese saline complex we carried out the oxidation of only simple double bond. So that can be oxidized to particularly beta oriented epoxy. So here we can write the reagents. We can use the manganese saline complex. Manganese saline complex is used. So for this condition is aqueous, sodium hypochlorite is used and solvent is the DCM dichloromethane. So this particular reagent, now this manganese saline complex containing this heterocyclic structure complexed with the manganese, and this complex act as the chiral reagent that will in presence of the aqueous sodium hypochlorite. So that will selectively carried out. It will react particularly at only beta direction or above the plane. Only one face is accessible. So front face of the double bond get reacted with the complex and oxygen present in the complex get delivered from the front face. So we are getting the beta oriented epoxide here. So this is the particular selective reagent given for this conversion. Now let us consider the second reaction. Now here carboxylic acid group is given, then alpha oriented and a substituent is given here which containing this double bond, and reagents are not given, and it is converted into the corresponding iodine. Iodine compound is here, and this acid is converted into lactone. That means this oxygen must react with the at this carbon atom, so that this 6-membered ring is synthesized here, or it is formed, and at this carbon iodine must be react. So lactone is formed from the double bond substrate containing the double bond and carboxylic acid. So this is hydrolactonization reaction. Already we have studied number of the reactions, number of examples for this reaction. So simply we can identify that carboxylic acid groups containing the proper double bond at the proper position get converted into corresponding lactone, iodolactone compounds. So this is hydrolactonization reaction. So reagent for this reaction is iodine in presence of sodium bicarbonate. Now in this case, the first step is the iodination. This is double bond, and this iodine acts as the electrophile here. So this double bond attacks the electrophilic iodine. This will get removed. And we are getting this. Now, if we consider the stereochemistry for this carbon atom, it is beta oriented. If it is beta oriented, that means attack of this carbonyl takes place from the front side, and this iodine carbon will goes on the back side or the below side. So as this group is present on the below side, this double bond react with the iodine from the below side or alpha side only. So alpha side is accessible for the reaction with this electrophile for this double bond, because on beta side carboxylic acid group is present. So approach of this iodine, it is not possible from the beta side or above side. So only back side or the below side it is accessible for the iodine. So we are getting the cyclic iodinium ion is formed. This is the formation of the cyclic iodinium ion on the below side or the alpha side. Now this oxygen, it is in close proximity. We can say this structure here, it is alpha oriented group is there. This oxygen now attacks this unstable ring. This is unstable ring, and this oxygen, as it is beta oriented group, it will attack from the front side or the above side to open this iodine. and then lactone, it is formed which containing this positive charge. So as desired in the product, we are getting the corresponding lactone. Only this hydrogen is present here, it will be removed easily to satisfy the valency, so we are getting this product. So this is very simple reaction, but we have to predict the proper stereochemistry, and we have to explain, or we have to give the proper orientation of these groups in the mechanism. So this is the hydrolactonization reaction. Now consider this third reaction. In this reaction, the substrate is not given and this acetyl chloride compound is given which containing the double bond, and again product is given here. Beta oriented methyl group is present and beta oriented phenyl group is present. So this we can identify this structure. So this is the part of this acid chloride acetyl group containing the double bond, and the remaining part, this ring system, it is already we have studied, it is the norepinephrine derived chiral auxiliary. We know that from norepinephrine compound we can synthesize, we have synthesized this compound and it acts as the chiral auxiliary. When it is attached to the substrate, so it influences the substrate and convert that into purely enantiomeric substrate. So your reactant or substrate becomes chiral, and this chiral compound can carry out the asymmetric synthesis. So this is norepinephrine derived chiral auxiliary. So we can write here structure. So this is the structure of the norepinephrine derived chiral auxiliary. When it reacts with this acid chloride, this nitrogen is found to be nucleophilic, it will displace this chlorine very easily. Reversal of the charge and chlorine will get removed, and we are getting this structure. So this is the first step of the reaction. Now in the second step, there is first treatment, first reagent is given. It is the LDA. LDA is the lithium diisopropyl amide compound, which is the strong base. Already we have studied number of times. So this is the structure of LDA, ionic compound, bulkier and very strong base. Now this base, it is found to be reacted with this double bond. So in this case, this is the second reagent. First reagent, it is the H2 in presence of the metal. So this H2 will carry out the hydrogenation reaction. So in this case, the double bond will get hydrogenate to the hydrocarbon, and then treatment will the LDA. These protons are found to be acidic. This can be removed by the LDA. Carbanion is formed here, and this carbanion is going to react with this electrophile, that is benzyl bromide. We know that it is SN1 as well as SN2 type of the electrophile. So we can write the mechanism here. In the first step, this double bond is get converted into simple hydrocarbon single bond, and we are getting this structure. This LDA will remove the acidic protons, and we are getting the corresponding lithium enolate is formed. Now this lithium enolate, it is stable compound. It is now ready to react with the benzyl bromide. So this benzyl bromide, now we have to predict the proper stereochemistry for the product. Now we can see the structure of the substrate. Methyl group and phenyl groups are orienting above side. They are beta oriented. They are present on the beta side, above side. So attack of this benzyl bromide or the electrophile on this double bond is not possible from the front face or above face because it is sterically hindered here. So this reagent will always react from this back side or below side or the alpha side. So we are getting the corresponding product. So this is negative charge. This carbon is nucleophilic. SN2 type of the reaction occurs. So this benzyl group is orienting downward side or alpha oriented benzyl group is present. So we are getting the product in which this alkylation reaction, after this alkylation reaction what happens? We are getting the alpha oriented benzyl group. It is not beta oriented. Selectively it reacts from the below side due to steric hindrance present on the above side. So this is the proper stereochemistry of the product. So now we stop here. Thanks for watching the video.